Good morning, students. So, in previous lecture, we discussed on payment, flexible payment design methods. Okay, so there are n number of methods. So, in our syllabus, we have these different methods which have been prescribed. And in previous lecture, we discussed on MacLeod method, and based on MacLeod method, we also solved a problem on that. Okay, so followed by that we'll be discussing on Kansas method in today's lecture, and we'll be also solving a problem on Kansas method. Okay, now Kansas method is also termed as triaxial method because the triaxial test results were extensively used in this method, so it is also termed as triaxial method. Fine. So we'll just understand what is the background of this particular method and how the equations were adopted in this particular method. Okay, so in the year 1910, Palmer and Barber, they proposed a design method based on Buzigny's displacement equation. Okay, now here Buzigny's displacement equation, it can be given by delta is equal to 3pa square divided by 2e into a square plus z square raised to 1 by 2. Now here P is the pressure, okay, pressure, and A is the radius of contact, and Z is the depth of the payment. Okay, so using this equation, they further took this equation and formulated a design equation. Okay, now here instead of pressure they have replaced with the load by the area. Okay, and Z is taken over here. Okay, so taking Z here, and we get this particular equation. Now assuming Z equal to T, assuming that payment is incompressible, Z is equal to T, and we get T equal to root of 3p divided by 2 pi es delta whole square minus a square to the whole to the power of root. Okay, so basically this equation of Buzigny's displacement equation was used to get this equation. Okay, so this was proposed by Palmer and Barber. Okay, now to this equation, the Kansas State Highway Department, they modified this particular equation, taking some coefficients into picture. Okay, now Kansas State Highway Department, they modified this particular empirical equation. Okay, so this was the theoretical equation. They introduced some empirical modifications. Now what were those modifications? The coefficients were taken into consideration, like traffic coefficient x and saturation coefficient y. Okay, so traffic parameter and saturation or the rainfall parameter was taken into consideration. So there was a modification in this particular equation. Now this multiplying constants were taken into consideration. So our equation of this, which was originally developed from Buzigny's displacement equation, were modified in this manner. So when this two coefficients were introduced, our TS will be root of 3p x and y. These were the additional modification, empirical modifications which were made. X y divided by 2 pi es delta whole square minus a square. Now this equation holds good when you have the modulus of elasticity for a single layer material. Okay, so where TS stands for pavement thickness in centimeter. Now this TS is pavement thickness in centimeter, and this capital P stands for wheel load in kg. And as I told, ES stands for modulus of elasticity of subgrade. Okay, from triaxial test results in kg per centimeter square. Fine. Then A is nothing but your radius of contact area in centimeter. Okay, and delta is the design deflection, Now as a default, this thing delta is taken as 0.25 centimeter. Okay, so this was the modified equations which was developed from Boussinesq displacement equation. Now further, if you want to consider the payment as two layer system, again there will be some addition to this particular equation. Now say if payment and subgrade are to be considered as two layered system, okay, a stiffness factor has to be introduced with different modulus of elasticity. Okay, so when we add this different modulus of elasticity for two layers, one is for subgrade and other is for payment, okay, then a stiffness factor is taken into consideration with es by ep whole raised to 1 by 3. Okay, so we'll be taking this consideration stiffness factor to the equation. Now our thickness of the payment will be the same equation what we got from the previous this thing, the multiplying stiffness factor taken into consideration. Why this came? Because the payment and subgrade are considered here, considered as two layered system. Okay, so stiffness factor is taken into consideration. So thickness of the payment is given by this equation. So thickness based on Kansas method, we have this equation. Fine. Then further, the relation between payment layers of thickness T1 and T2 of elastic modulus E1 and E2 is given by T1 by T2 is equal to E2 by E1 whole raised to 1 by 3. Okay. So further this relation also comes into picture. Okay. Then based on this equation of Kansas, okay, originally it was a Boussinesq or single layer theory which they adopted further, you considering the coefficients or empirical coefficients of traffic and saturation or rainfall factor into consideration. Okay, now this x and y are based, or there are recommended values for these particular coefficients. Okay, we can see over here the recommended values of coefficient x and y are based on average daily traffic of design traffic and rainfall data. Okay, let us see. So if we need to consider a traffic coefficient as 0.5 or 1 by 2, our average daily traffic in numbers is 40 to 400. For example, if you have the average daily traffic on the road in between 40 to 400, then your x value we need to consider as 1 by 2. Likewise, if your average daily traffic is lying in between 401 to 800, then the coefficient taken in place of x is 2 by 3. Okay, likewise for the other traffic parameters or conditions. Okay, likewise the y coefficient, that is nothing but the saturation coefficient, or it is also the rainfall coefficient, is based on average annual rainfall in centimeter. If that particular area is having 38 to 50 centimeter of rainfall, annual rainfall, average annual rainfall, then coefficient taken is 0.5. Okay, likewise for other rainfall datas we can take the y coefficient subsequently. Okay, so these are the traffic coefficients and rainfall coefficient recommended values by Kansas department. So these were the values which will be adopted for your coefficients. Let us solve a problem on Kansas method or triaxial test method. Okay, so this is a problem. Design the payment section by Kansas method using the following data. Okay, so let us see what are the data given here. A wheel load of 4100 kg, radius of contact area, that is the value of small a given as 15 centimeter, and traffic coefficient is nothing but the x value which is given by 1.5, rainfall coefficient nothing but y value, it is 0.9. Now here either they give the traffic coefficient directly with these values, or when we are seeing the recommended values, okay, so either they give the average daily traffic, okay, number of vehicles, or they give the rainfall annual average annual rainfall data in terms of centimeter of that particular area. If they give that data, we need to convert those data into coefficient values, okay. So that table will be given to you, the traffic counts. Based on that traffic count, we can adopt this particular coefficients. Now in this numerical, they are directly given the coefficients. Now design deflection delta, as I told you, default value is 0.25 centimeters. Now if not given, you can adopt this value. If given any other deflection value, design deflection, you can adopt that. Now as of now, it is 0.25, delta value 0.25. Now E value of subgrade soil, modulus of elasticity of subgrade soil is 100 kg per centimeter square, and modulus of elasticity of base course is 400 kg per centimeter square. And additional data of E value of 7.5 centimeter thick bituminous concrete course is given by 1000 kg per centimeter. So carefully we need to understand what is the given data to solve this particular payment section, okay. Then going to solution, we will be finding out the thickness of the payment. Now solution. Now first, assuming the payment to consist of single layer base course. So assuming the payment of single layer base course material, the thickness TB, I just write it as thickness of base course TB is equal to, the same equation will be using here. So root of 3pxy divided by 2 pi s delta minus a square, close this flower bracket, multiplied by stiffness factor we need to consider. S is represented by modulus of subgrade to the modulus of base course, okay, EB. This whole raised to 1 by 3. So this is the equation we will be finding out the thickness. So here carefully we need to substitute the values. All these unknown quantities are given in the form of data here. So 3 P stands for the wheel load. So this is the P value, and this stands for small a, radius of contact area. Traffic coefficient is given, that is the value of x. Rainfall coefficient is given by y, capital Y. Design deflection is nothing but the delta value, and this subgrade, it is given by ES. Modulus of subgrade is given by ES, and this is EB, modulus of base course, okay. So all these given values we need to substitute here. So this is 4100 multiplied by x value is nothing but coefficient of traffic multiplied by 0.9. 2 pi es is given with 100, and delta value is nothing but the deflection 0.25 minus a square is nothing but radius of contact area is given by 15 centimeters. So close this bracket. Then we have ES value as 100 divided by EP value by 400 whole raised to, sorry, this is 1 by 3 whole raised to 1 by 3. Okay, so when we calculate this in calculator, we get a value of 104.64. This value I get it as 104.64, and this value I get it as 0.63. Okay, when I multiply these two values, I get a thickness value TB as 65.9 centimeters. So assuming the payment as a single layer base course TB, I have calculated this value taking this equation and substituting all the values from the given data. I get a thickness of 65.9 centimeter. Now you need to remember, this is as a single layer base course material. We got it as 65.9 centimeter. Fine. Now further moving, there was an additional data which is given. E value of 7.5 centimeter thick bituminous concrete course of 1000 kg per centimeter square. Okay. Now taking that into consideration, let 7.5 centimeter bituminous concrete surface with modulus of this material is 1000 kg per centimeter square be equivalent to thickness TB of base course. Now taking that relation what we discussed from the Kansas method, so T1 by T2 I will be writing as thickness of base course by thickness of bituminous concrete. We represent it by TC, thickness of base course to the thickness of bituminous concrete, that is TC equal to, this was E2 by E1. Instead of writing E2 by E1, I will be taking as modulus of elasticity of the bituminous concrete by modulus of elasticity of the base course whole raised to 1 by 3. Okay. Now taking this into consideration, so we know the values here. So taking TB on the left hand side, EC value from the given data is 1000. EB value also we know, that is 400 kg per centimeter square, to 1 by 3. Now we know this particular thickness value 7.5 centimeter is given. So taking this value of TC is equal to 7.5. Okay, so we can find out TB is equal to 10.2 centimeter. So we have found out the bituminous concrete surface equivalent to base course. This value we have got. Okay, now the required base course thickness will be, therefore required base course thickness is equal to this value 65.9 centimeter minus 10.2 centimeter. So when you subtract 10 centimeter from this value, 55.7 centimeters is the required base course. Okay, so our payment section consists of 55.7 centimeter as base course. This we can take it as WBM, waterborne macadam layer, and 7.5 centimeter of bituminous concrete. Okay, so the same can be represented in a payment section with a line diagram. So just a simple line diagram showing the first layer as the bituminous concrete of 7.5 centimeter, bituminous concrete of modulus of elasticity as 1000 kg per centimeter square, and then a base course of 55.7 centimeter with base course with modulus of elasticity of 400 kg per centimeter square, and then below this will be your soil subgrade. Below this will be the soil subgrade with modulus of elasticity will be 100 kg per centimeter square. So finally we need to go for this line diagram and show the thickness of each layer. So this is how we need to solve the problem. Very simple.